Bismillah ar-Rahman ar-Rahim. We are interested in the integral from 0 to 1 of the square of the fractional part of 1 over x times the fractional part of 1 over 1 minus x. Let's start by doing the change of variables. Y equal to 1 over x. When x is equal to 1, y is equal to 1. When x tends to 0, y tends to infinity. Dx is minus 1 over y squared dy. 1 over x is replaced by y. 1 over 1 minus x is 1 over 1 minus 1 over y. Multiplying the numerator and denominator by y, we get y over y minus 1. We split the integral into an integral from 1 to 2, which is this one, plus an integral from 2 to 3, 3 to 4, and so on. All those integrals are given by this omega 1, summation v from 2 to infinity, integral from v to v plus 1, the square of the fractional part of y, multiplied by the fractional part of y over y minus 1, then dy over y squared. Y over y minus 1 is greater than 1. The minimum value of y here is 2. When y is greater than 2, y over y minus 1 is less than 2. If y is greater than 2, add y to both sides. So we have 2y greater than y plus 2, which means that 2y minus 2 is greater than y. 2 times y minus 1 between brackets is greater than y. So y over y minus 1 is less than 2. In all these integrals here, this number is between 1 and 2. The fractional part of y over y minus 1 is y over y minus 1 minus 1. This is the key here in tackling omega 1. Also, the fractional part of y is y minus the floor of y. And if y is between v and v plus 1, then the floor is equal to v. Combining these two ideas, the integrand here becomes y minus v squared divided by y squared times y over y minus 1 minus 1. This is y minus 1 in the denominator, and in the numerator we have y minus 1. That's 1. This is the integrand, y minus v squared upstairs. Downstairs we have y squared times y minus 1. When we expand the numerator, we have y squared, and we have y squared in the denominator, so we have 1 over y minus 1. We also have v squared. We get v squared divided by y squared times y minus 1. And then there is minus 2yv in the numerator, which is minus 2v. And then in the denominator, we have y times y minus 1. The integral of 1 over y minus 1, that's the natural logarithm of y minus 1. When we use the limits of integration, this is len v plus 1 minus 1, that's len v minus len v minus 1, which is len v over v minus 1. V squared divided by y squared times y minus 1 can be written as v squared. And then we have a bracket with 3 terms, 1 over y minus 1 minus 1 over y minus 1 over y squared. When we integrate, this gives us len v over v minus 1. When we integrate this guy, we get len v plus 1 over v. This is minus y to the minus 2. When we integrate, we get y to the minus 1. Using the limits of integration, we get 1 over v plus 1 minus 1 over v. Here we have minus 2v. 1 over y times y minus 1 can be written as 1 over y minus 1 minus 1 over y. Integrating, we get len v over v minus 1 and len v plus 1 over v. This part here, omega 1, is given by this summation, which can be simplified. Len v over v minus 1 appears here with coefficient 1. Here it is multiplied by v squared. And here there is minus 2v. This logarithm is multiplied by v minus 1 squared. Len v plus 1 over v, it has here minus v squared, and from here plus 2v, so that's minus between brackets v squared minus 2v. These two guys together give us minus 1 over v times v plus 1. Then there is this v square, so we get minus v over v plus 1. This is omega 1. Now we go to omega 2, which is the integral from 1 to 2. First, let's do the substitution. Y equal to 1 plus t. Every y here is replaced by 1 plus t. The limits of integration become from 0 to 1. If we have a real number t with some fractional part, adding an integer to t does not change the fractional part. We can exploit this fact here. We have the fractional part of t plus 1. That's exactly the fractional part of t. When y is replaced by t plus 1, y over y minus 1 becomes t plus 1 divided by t. That's 1 plus 1 over t. The fractional part of 1 plus 1 over t is the fractional part of 1 over t. T is a number between 0 and 1. The fractional part of t is exactly equal to t. Now we have an integral from 0 to 1. The integrand is t squared divided by 1 plus t all squared, then the fractional part of 1 over t. Let's do another substitution. T is replaced by 1 over u. When t is 1, u is 1. When t tends to 0, u tends to infinity. Dt is minus du over u squared. this ratio here becomes 1 over u squared divided by 1 plus 1 over u all squared. We can multiply inside the bracket by u to get u plus 1 all squared. The integrand is the fractional part of u divided by u squared, u plus 1 squared. The integral here can be written as a sum over positive integer v from v to v plus 1. The fractional part of u is u minus the floor of u. Since u is between v and v plus 1, the floor is equal to v. The integrand is 1 over u times u plus 1 squared minus v over u squared, u plus 1 squared. 1 over u times the square of u plus 1 can be written as such. Similarly, 1 over u squared, u plus 1 squared can be written using these four terms. We do the integrals as above, then simplify to obtain this summation for omega 2. So far, the integral of interest is given by omega 1 plus omega 2. To combine the two omegas, we revisit omega 1 and change the summation index v to v plus 1. When v is changed to v plus 1, the summation is from 1 to infinity. Every v here is replaced by v plus 1. Now the two sums are from 1 to infinity. We can add them. This is what we get. Note that len v plus 1 over v, here it's multiplied by 2v plus 1. There it's multiplied by v squared. Together they give v plus 1 all squared. Len v plus 2 over v plus 1. From here we have minus 2v minus 1. There we have minus v squared plus 1. This logarithm is multiplied by minus between brackets v squared plus 2v. V plus 1 over v plus 2 can be written as v plus 2 minus 1 over v plus 2. That's minus 1 plus 1 over v plus 2. Minus 1 is here, plus 1 over v plus 2 goes away with this. Then we have minus 1 over v plus 1. Our problem now is to obtain this summation. We take the sum from 1 to n and then take the limit as n tends to infinity. Note that we have summation v from 1 to n of minus 1. This is equal to minus n. Then we have minus summation v from 1 to n, 1 over v plus 1. This is minus between brackets 1 over 2 plus 1 over 3 all the way to 1 over n plus 1. We can add 1 over 1. So there is an extra minus 1. So we add 1 here. This is this one here. We have the harmonic number hn plus 1. From the harmonic number, we subtract len n plus 1. Because there is a minus sign here, then we need to have minus len n plus 1. We do this because we know that the limit as m tends to infinity, h of m minus len m is equal to gamma, the Euler Mascheroni constant. We have handled these two guys here. What about the terms with logarithms? Let's focus on them. Separate the summation into two sums. In this summation here, replace v by v minus 1. The goal is to have this logarithm change it to the logarithm of v plus 1 divided by v, like this one. When we do this change, v is from 2 to n plus 1. The logarithm is multiplied by v squared minus 1. We can start the summation from 1 because the extra term is equal to 0. Now we can recombine the two sums, noting that this summation has an extra term when v is equal to n plus 1. Let's write this extra term here. We have minus between brackets n plus 1 squared minus 1 len n plus 2 over n plus 1. Then when we combine the sums, we have len v plus 1 divided by v. From here we have v squared plus 2v plus 1. From there we have minus v squared plus 1. These two guys cancel and we are left with 2v plus 2. This summation is equal to 2 times summation v from 1 to n, v plus 1 len v plus 1 minus len v. Let's investigate this summation. The summand is v plus 1 len v plus 1 minus v plus 1 len v. This can be written as minus v len v minus len v. The idea here is to have a telescopic sum. The surviving terms when we do this summation, this term when v is equal to n, that's n plus 1 len n plus 1, and this term when v is equal to 1 minus 1 len 1 is equal to 0. This summation is equal to n plus 1 len n plus 1 minus the sum of the logarithms, which is the logarithm of the product, and the product is n factorial. Our result involves these two terms after multiplying them by 2. Okay, we are getting close. We have minus gamma from here. We have this one, and then we have the limit as n tends to infinity of these terms involving n. Let's deal with the factorial. We can make use of Stirling's bounds. N factorial is upper bounded by square root 2 pi n, n to the power n e to the minus n, e to the power 1 over 12n, and is lower bounded by square root 2 pi n, n to the n, e to the minus n, e to the 1 over 12n plus 1. This means that the natural logarithm of the factorial of n is the natural logarithm of square root 2 pi n, which is 1/2 the logarithm of 2 pi plus 1/2 the logarithm of n. Then we have n log n. Then we have minus n, this exponential in the lower bound and this exponential in the upper bound, mean that we have big O of 1 over n. The logarithm of n factorial is multiplied by minus 2. So we get minus ln 2 pi minus ln n minus 2n ln n plus 2n. Then we copy and paste the other terms. This one is minus 2n plus 1 ln n, and this is 2n plus 1 ln n plus 1. These two guys can be combined as 2n plus 1 ln n plus 1 over n, which is 2n plus 1 ln 1 plus 1 over n. 2n minus n is n. This n plus 2 can be written as n plus 1 plus 1. We have the natural logarithm of 1 plus 1 over n plus 1. The Taylor series of ln 1 plus alpha about 0 is alpha minus alpha squared over 2 plus big O of alpha cubed. We have here 1 over n and there 1 over n plus 1. These terms approach 0 as n tends to infinity. We can write down this logarithm as 1 over n minus 1/2 times 1 over n squared plus big O of 1 over n cubed. We handle this logarithm in a similar way. Let's see what we have. We have 2n plus 1 divided by n. We have minus 1/2 2n plus 1 over n squared. This goes to 0 as n tends to infinity. 2n plus 1 times something of order 1 over n cubed also tends to 0 as n tends to infinity. From this part here, we get 2. Let's go here. We have n minus n squared plus 2n over n plus 1 plus n squared plus 2n over 2n plus 1 squared. This is quadratic in n. We have here big O of 1 over n cubed. So this product goes to 0 as n tends to infinity. What about those terms? From here, as n tends to infinity, we get 1/2. These two guys, we need to combine them. And when they are combined, they give us n squared plus n minus n squared minus 2n over n plus 1. This is minus n over n plus 1. We get minus 1 when n tends to infinity. All in all, we get 2 minus 1, that's 1, plus 1/2, that's 3 over 2. 3 over 2 plus 1, that's 5 over 2. Our final result is 5 over 2 minus the Euler Mascheroni constant minus the natural logarithm of 2 pi.